if this is the polarity that we chose, like this is VP, this is VN. Here, VN is bigger than VP, so our output is going to be 0. Then VP becomes bigger than VN, we're going to have positive. Then becomes 0, becomes positive, becomes 0, right? This is VN, yeah. And then becomes positive, and becomes negative, becomes positive, becomes negative, and so on. So this is how we generate a PWM signal. This is like sinusoidal PWM. Okay, so for example, in the case of unipolar, or sorry, in the case of bipolar modulation, you remember that we only had one comparator for the bipolar modulation, right? So that would be it, right? This is like how we generate those signals, and whatever we have, this is gonna be, let's say, S1 and S2, and the complementary of that would be S3 and S4. Let me write S4 and S3. S4, S3, yeah. So this is basically how, this is like what you apply to those switches to turn them on and off. Okay, so this is basically what's happening in the bipolar modulation. Now I want to do the same thing for unipolar. This is the whole concept of bipolar modulation. So one question I have from you guys, the output that we get, what is the frequency of that output? Let's say like this is 60 Hertz. This is 1 kilohertz. What's going to be the frequency of output, 60 Hertz or 1 kilohertz? It's going to be 60 Hertz, right? Because you have the slower signal would take over, right? So like the frequency of the output is 60 Hertz. So this modulating signal, this is called modulating signal. Would have the frequency that you want to have in your AC voltage, and this is called carrier signal. This would determine like the switching frequency. This would determine the switching frequency. Now what I did for you guys, I did this triangular waveform and a sinusoidal waveform like this, right? So this would have frequency, and then this one would have a frequency. I'm just doing the period, right? This is like, let's say, modulating signal. And this one would have an amplitude, and this one would have an amplitude. We're gonna see the impact of these amplitudes and these frequencies on the output voltage a little bit later in future video. So, but that's very important, right? Like if, let's say, like if my in one of the labs for ELEX 3130, some of the students were supposed to do this, right? And what they did, they didn't notice that their sinusoidal wave had a DC offset. So this was their sinusoidal input, and this was the triangular waveform. It's always bigger than this one, right? So that's always going to be on. It's always going to be the positive VCC, right? Or like, if that's the case, if this is what we have, right? If the amplitude of this one is much bigger than this one, right? Then that's not going to work, right? So we're going to see the impact of the amplitude and frequency of modulating signal and the carrier signal in a future video. But for now, let's see how unipolar modulation works. You remember that for bipolar modulation, we only need one comparator. We only create the gate signal for one of the switches, and the other switch on the same leg would have the complementary of that one, and the other switch in the upper half also has the complementary of S1, and S2 has the same. So we would basically just create one PWM signal. In unipolar, we would have two different PWMs, because you remember that we had let's say like two switches. This is our load, right? This is S1, this is S3, this is S2, this is S4. We had four switches, right? In unipolar, this leg and this leg would be independent. Okay, so we need to fire them independent from each other. So we need to have two comparators. The way PWM takes care of that, it's like having one sinusoidal here going to one comparator, and we have the carrier signal here. We will have another comparator. Again, let's say this is 0. That would have exactly the same carrier.